I'm Andrew Bazarko. I'm the Simons Observatory project manager. So a little bit about my background. I was a graduate student in experimental particle physics, and so after doing PhD work, it was actually I worked at the Stanford Linear Accelerator Center. I did my data analysis on data from a project at Fermilab. Then I went off and did a postdoc at CERN. And then I came back and did academic work in experiments that happened at Brookhaven National Lab, and then again in an experiment at Fermilab. So over my career as an experimental particle physicist, I think I visited most of the high energy physics labs that exist in the world. And then I moved into industry. And I spent a little over a decade working in industry, doing research and development, and I got into management. And so at that point, the opportunity came along to join the Simons Observatory. It was a very exciting project. And so in about 3 years ago, I joined the Simons Observatory to become the project manager. My most recent research projects, when I was after my postdoc, I worked on a rare kaon decay experiment at Brookhaven National Lab. So we were looking for a decay of the K plus, the positive kaon, to a pion and 2 neutrinos. So this is a decay that's forbidden to first order in the standard model. And so after a long, hard search, we finally found the first example of this decay. 1 in 10 to the 10th kaons decays at this level. So that's very interesting, but unfortunately, that's at about the level that the standard model predicts. The exciting thing would have been if we had seen it occurring somewhere outside the standard model. And after that, my experiment at Fermilab was searching for neutrino oscillations. So with an accelerator, you produce a neutrino of one flavor at the source, and you put your detector downstream and look to see if that neutrino has changed flavors by the time it interacts in your detector. My work has been with neutrinos as a particle physicist, and now working on the CMB, I'm kind of interested in seeing how the CMB can constrain the mass of the neutrinos that we tried to constrain in the laboratory, but we look out in the universe and get similar information about neutrinos. We're building an observatory in the Atacama Desert of Chile. This is at a location where researchers have worked before. And in fact, our project, of course, takes the team working on the Atacama Cosmology Telescope, takes the team working on Polar Bear Simons Array, has everybody work together to build a new facility with unprecedented sensitivity to study the cosmic microwave background. So the project manager's job, and project management, there's the so-called iron triangle. The legs of the triangle are schedule, scope, and budget. And the notion is that you want to keep all those where they are, and if anything starts to slip, one side starts to slip, the whole triangle gets distorted. You can't achieve more scope unless you have more schedule and budget. This kind of thing. So we try to do as best we can on tracking schedule, budget, and scope to try to deliver the project on time, on budget, and delivering the scope that we promised. Very challenging on all fronts. We've taken our project and we've broken it down into 8 work areas. The Large Aperture Telescope, which is a 6-meter large aperture telescope for doing high-resolution observations. We have the Large Aperture Telescope Receiver. That's the second work package. This is the camera that will be mounted on the Large Aperture Telescope. The third work package are the Small Aperture Telescope platforms. We're building 3 small aperture telescopes. Each one of them is on a platform to let it move. The fourth work package are the 3 cameras that go on these platforms, so the 3 small aperture telescopes. The 5th work package are the detectors and readout. So these are the fine instruments that actually become the focal planes of these cameras. The 6th work package is the data management. So it's all the computing, data movement, and the software that takes the data from the cameras and basically reduces it and ships it to the data centers. The 7th work package is actually all the infrastructure at the site. So everything that we're building in the Atacama Desert, buildings, roads, foundations for the telescopes. And then the 8th work package we call integration and test. So this is a work package that considers the system integration, making sure things are calibrated, and making sure we meet the requirements that we're setting out to meet. Yeah, so here we are. I'm speaking to you in October 2019. So let's just consider some of the big things coming up for the project over the next few months. So for the Large Aperture Telescope, the Large Aperture Telescope is finishing the design phase with our contractor, a company called Vertex, based in Germany. So we will have the final design review for the Large Aperture Telescope at the end of November, and so that will launch the production stage, the manufacturing stage of the Large Aperture Telescope, and we expect about a year from now to see a telescope constructed in Europe, going through final acceptance tests to then be dismantled and shipped to our site in Chile. For the camera that goes on the Large Aperture Telescope, the large cryostat for that camera, it's the largest camera for CMB observations that's ever been built. That cryostat exists at the University of Pennsylvania, and it's going through its first stages of cryogenic validation. So over the next month or two, the group there will install the dilution refrigerator and demonstrate that this refrigerator can get down to its operating temperature of 1/10 of a degree Kelvin above absolute zero. For the small aperture telescopes, we have the first example. The first cryostat is actually in the lab here at the University of California, San Diego, where I'm visiting today. And the group is doing similar things that I just described for the Large Aperture Telescope receiver. They're going through the cryogenic validation of the small aperture telescope, and over the next few months we'll continue to instrument it so that we expect that by March, April of the coming year, the small aperture telescope will be ready to receive its first example of detector and readout modules to start completing the validation of the entire system, start doing dark tests with those detectors and readout, and then going on to optical tests to get this instrument ready to be shipped down to Chile. So it's a stage of the project now where we're really seeing the fruits of all the design and planning come together with instruments in the laboratory and gearing up to start sending them to Chile. So it's a very exciting time in the project.